Hi everyone. To get us started in Unit 4, we're going to be talking about velocity and other rates of change. So this is a really big topic in AP Calc and will definitely be on the AP exam. So we're going to be working through this topic over the next several days. So to get us started, we're going to be working with some of the really important vocabulary and showing you examples of how we apply it in calculus. So the first thing we have here is what we call the position function. So the position function for an object moving along a line, say the x-axis, describes the location of the object at any given time. So when we're talking about these problems, we're really thinking about, here's our x-axis, we're talking about some particle and its movement back and forth along that line, and we need ways to be able to analyze that. So the position function is going to tell us the location of the object at any given time. In terms of symbols for the position function, a lot of times you'll see it referenced as s of t, or sometimes they'll call that position function x of t. So I think here a lot we use s of t to denote the position function, but realize x of t can be used as well. So in question 1, it says the position function for a particle moving along a horizontal line is given by this function here. So there's my position function. It tells me that s is measured in meters and t is measured in seconds, and it wants us to find the position of the particle at time t equals 3. So in this case, since I'm looking for the position, and they gave us the position function, all we need to do is substitute 3. So I'm going to take my function s and I'm going to plug in 3 for t. So I'm going to get s of 3 is negative 2 times 3 cubed plus 3 times 3 squared. And now we just need to evaluate it. So 3 cubed I know is 27 times a negative 2 is a negative 54. Plus 3 squared is 9 times 3 is 27. So if I add negative 54 plus 27, I'm going to get negative 27. And my units, it says s is measured in meters. So my units are meters. So s of 3 is negative 27 meters. Now, sometimes people get thrown off by the negative. What that means in this context is that our particle, actually let me see, the location of the particle at time t equals 3, and that was t equals 3 seconds, is 27 meters to the left of the origin. So don't get kind of freaked out by that negative. All that negative means here is that I'm to the left of the origin, and that'll come into play maybe in a couple days. We'll be referencing back to that. But the big idea here is if I want the position, I just use my position function. So our next term that we need to be familiar with is displacement. Now the displacement of an object just describes how far an object is from where it started. Now with displacement, we're always going to be looking at the displacement over an interval. So if I want to compare where it is compared to where it started, we'll have to look at an interval of time. And for this one, all we're going to be looking at is we're going to be comparing, let's say my interval is from t1 to t2. And I want to know the displacement of the object over that interval. All we're going to do is take the position at time 2 and subtract the position at time 1. So again, we have the same function here, the same position function. Now it's asking us to find the displacement of the particle, and again, here's this interval from 0 to 3. So in this case, my time 2 is 3, so I'm going to take s of 3 minus time 2 is s of 0, and then we'll do that calculation. Well, we actually already figured out s of 3 above. We knew that was negative 27 minus, if I plug in 0, s of 0 is just 0. So we get negative 27, and again, my units are meters. So here again, we see that negative 27. So in the context of displacement, what that tells us is that the particle is 27 meters to the left of where it started. So that sign is telling us about the direction. So to the left of where it started, and again, left because that's negative. Okay, so I'm going to make a note here that the sign tells how far right or left the particle is from where it started. So if the sign is positive, it's to the right of where it started. If it's negative, sorry, I'm squeezing that in there, it's to the left of where it started. All right, let's keep going. We have lots of vocab here. The next one is average velocity. And so the average velocity of an object over a given time interval describes the average rate of change of the object. Hopefully by now, when you hear average rate of change, you should just be thinking about our regular slope formula. In this case, since we want average velocity, it's going to be the slope of position in particular. So again, average velocity always has to be over an interval. So when we're looking, let's again call that interval just from time 1 to time 2. Then our average, I'm going to use that abbreviation, average velocity is just equal to the position of time 2 minus the position at time 1 over time 2 minus time 1. And the sign of the velocity is going to tell us the direction that the object is moving. Okay. So let's see what our question is here. Same function, it asks us to find the average velocity of the particle over the time interval from 0 to 3. So again, this is our t1 and our t2. So our average velocity is going to be s of 3 minus s of 0 over 3 minus 0. So there's that s of 3 again, and if we were to flip back, that was negative 27. S of 0 is just 0 all over 3, so we get negative 27 over 3, which is equal to negative 9. Now, here we have to be careful with our units. In this case, our numerator was position, that was meter. Our denominator is the change in the time, its units were seconds, so our units are meters per second. So this tells us that our velocity is negative 9 meters per second. We know, since that's negative, that our object is moving to the left. And I'm actually a little bit ahead of myself there. We'll talk about that more in a minute. Okay, instantaneous velocity. Hopefully that word instantaneous has already clued you into the fact that we're talking about a derivative here. So we're talking about instantaneous velocity means a single point in time. We're not looking at an interval anymore. We're talking about what's happening at a single point in time. So the instantaneous velocity is the derivative of the position function. And it's going to tell us how fast an object is moving, again, at a moment in time. And for notation, we use v of t, and we know that's just equal to s prime of t. Velocity is the derivative of position. All right, so let's see here. Now we're being asked, what is the velocity of the particle at time t equals 3? So I know velocity is the derivative of position. So before I worry about the specific time, I'm going to get my velocity function. So v of t is just equal to s prime of t, and this is a nice, just easy power rule. We have negative 6t squared plus 6t. So that's our velocity function. Now at time t equals 3, I'm just going to plug in 3. So I get negative 6 times 3 squared plus 6 times 3. So what do we have here? Negative 54 plus 18. And we get negative 36. And again, because our derivative is a rate, we have to be careful with our units here. Our units are still going to be meters per second. Oh, I'm sorry, you can't see that. Let me scooch that up. Again, those units are meters per second because we know our derivative is a rate. Okay. Now we're going to really start here. We've learned kind of all the functions, so we've got position and velocity so far. Now we're going to talk a little bit about how we can use those to describe the motion of our particle. So when we're trying to decide the direction an object is traveling, we look at the sign of the velocity function. And we're going to be making a table to help us do that. And so I already alluded to this a little bit, but when we're talking about direction, so for example, if I want to know where the particle is moving right, I'm looking for where velocity is greater than or equal to 0. If I want to know where it's moving left, we're looking for where velocity is less than or equal to 0. And if I want to know where it stopped, that's where velocity is equal to 0. So let's see how we're going to use all of that. We have our same position function for our same particle, and we want to know when is the object moving right, left, or stopped. And we're going to show our work here to justify our answers. So here's how this is going to go. I know that to answer this question, I need a velocity function. So the first thing I'm going to do is take my velocity function, which again is negative 6t squared plus 6t. Now, I'm going to take that velocity function and I'm going to set it equal to 0. Now, I know that 0 is actually going to tell me where this particle is stopped. But that's also going to tell me where the particle changes direction. I know to change from going from right to left, I have to be 0 in between. So this is going to help me divide up the time intervals so that I can ultimately decide when I'm moving right, left, or stopped. So let's deal with this first. So I'm going to factor out a negative 6t. So that means inside I'm going to have t minus 1, and that's equal to 0. So that tells me either negative 6t is equal to 0 or I got a little bit ahead of myself there, or t minus 1 equals 0. So that tells me my velocity is 0 when t equals 0 or t equals 1. So what I'm going to do with that is I'm going to make a little table here for velocity. I'm going to use a number line. And so I know my key points here are 0, so let me draw this down here, and 1. At these 2 points, my velocity is 0. But my goal here is to figure out where it's moving right and where it's moving left. So I have to figure out the sign of velocity on these 2 intervals. Now you'll notice I'm not looking at time less than 0. Since this is time measured in seconds, we don't talk about negative seconds. So I'm starting my interval just looking at, I should make a note here, really for t greater than or equal to 0, since we're talking about time. So I know at these 2 points velocity is 0. So I need to figure out what's going on in between. So let's look at, I'm going to pick, let's say, at time 1/2, because I know that's in this interval. Now, if I want to know the sign of velocity, I think it's easiest to go back to this factored form. So here's what I'm going to do. I know -6 times a positive 1/2. Negative times positive, that makes this factor negative. 1/2 minus 1 is going to be negative. So I have a negative times a negative. That's going to make this velocity positive over this interval. Now I'm going to pick a number greater than 1. Let's say 2. And again, I'm going to go back. I need to know the sign of velocity. So let's look at our factored form. -6 times 2 gives me a negative number. 2 minus 1 is 1, which is positive. So a negative times a positive gives me a negative. And now I know the signs. I know that here my object is moving to the right. And then on this interval, my object is moving left. So to answer the question, we've done our work to justify it. Now we just need to state the intervals. We're moving right on the interval from 0 to 1. And you'll notice I made those closed brackets because we defined right as greater than or equal to 0. So I include 0 and 1. We're moving left then on the interval from 1 to infinity. And then we're stopped where it's equal to 0, which is really where we kind of started our calculations. It stopped at time t equals 0 and 1. All right. Next up is speed. So the speed of an object is the absolute value of the velocity. So for speed, we're looking at how fast an object is going. It shouldn't say and, but how fast an object is going, and we're ignoring the direction of travel. So in terms of notation here, we're just talking about the absolute value of velocity. So for this example, if I want the speed of the particle at time t equals 3 seconds, the first thing I'm going to do is just calculate my velocity at time 3. And we had actually done that at some point. Oh, if you look at question 4, we found out the velocity at 3 was -36. Now that tells me the velocity. So if I want speed, that's going to be the absolute value of -36, which is just 36. And again, my units are meters per second. All right, we are almost there. Thank you for hanging in with me so far. All right, one more function here, acceleration. So the acceleration of an object describes how fast the velocity is changing. So we can talk about the rate of change of the velocity. Since I want a rate of change, it's just the derivative of velocity with respect to time. So acceleration is just the first derivative of velocity, which also means it's the second derivative of position. So if I want the acceleration of the rock at t equals 3, right, our position is -2t cubed plus 3t squared. That tells me my velocity is -6t squared plus 6t, which means my acceleration, let's see, is -12t plus 6. So now if I want the acceleration, a of 3 equals -12 times 3 plus 6. So I get negative 36 plus 6 is negative 30. Now with the units, we have to be careful. So we said it was the rate of change of velocity. So velocity was meters per second, and then we're talking about the rate of change of that with respect to time. So meters per second, or what we'll often say is meters per second squared. All right, and the last piece of this now is talking about how do we know when an object is speeding up or slowing down, or we could talk about whether its speed is increasing or decreasing. So we can tell an object is speeding up by looking at both the velocity and acceleration functions. So if velocity and acceleration have the same sign, that means both positive or both negative. If they have the same sign, then the object is speeding up. So both negative or both positive means the object is speeding up. If they have opposite signs, one is positive and one's negative, then the object is slowing down. All right, so our question here, back to our same old position function, is asking us, is our particle speeding up or slowing down at time t equals 3? So I know I need to compare two things. I need to compare the velocity at time 3. That value we knew, I have to peek back because I don't remember it. The velocity at 3 was negative 36 meters per second. The acceleration at time 3 we just found, that's negative 30 meters per second squared. So what I notice is that both of these signs are negative. Since they're both negative, the object, our particle, is speeding up at t equals 3. And I would say because v of 3 is less than 0 and a of 3 is less than 0. So same sign tells me that they're speeding up. All right, I apologize for the long video. I know that was a lot, but you'll have some time in class then to process this and work through some problems. All right, thanks for hanging in there. Make note of anything you have questions on, and we'll address that when we're back in class. Thank you.